Alright you guys, hello, welcome back. Today what I'm going to do is extend the concept of what we talked about in the prior video, which is looking at derivatives as a function. So in the prior video we talked about derivatives at a particular point on a graph. So again, just a quick refresher. If I draw some function f of x, we talked about having some point where we wanted the tangent line. Let me switch colors for a moment, right? So let's say we wanted the tangent line at the point x equals a, right? So our approach was we moved some distance away, called it a plus h. We took this point on the graph and we slid it closer and closer to the point of tangency. So we did a limit process, right? So the derivative at a, we said, was the change in y values, right? The delta y over delta x. So that was the slope of the secant line, and when we took a limit as h went to 0, that was the slope of the tangent line. Now, when we discussed this in the prior video, right, what we talked about is this value a was a specific number within the domain of the function. So this could have been x equals 1. So we were finding the derivative at 1. And so we were plugging 1 in for our a value. We could have found the slope of the tangent at x equals 5, right? So the a was the 5 value, and we were plugging 5 into our formula. So that was our approach in the prior video. We were finding slopes of tangent at a specific value. And what we want to discuss in this video is, what if we're letting this x value be anything that it wants? And we kind of talked about it in that prior video, but we didn't make the generalization or the abstraction. So instead of calling this a specific number a, why don't we call this any value of x? So the a value really is in essence allowed to be anything it wants within the domain of the function. So again, if I just redraw this graph, instead of calling this a specific number a, let's call it any number x within the domain of the function. So we really have the exact same definition that we had in the prior section, right? So we want the slope of the tangent. So what we're going to do is move some distance h away. This point will slide to this point, so our secant line becomes our tangent line. So again, the only real difference is our formula looks a little bit different, but conceptually it's the exact same thing in our prior video, right? So we're just abstracting to the fact that every value of x in the domain of the function can have a slope of a tangent. There's an exception to that rule, and we'll talk about that in a minute. But let's talk about the function derivative form. Right? So in other words, the function f of x that we've drawn here, it has a derivative. And if we plot every tangent to this graph, that creates the graph of the derivative. All right, now I'm going to do my best to, let's not forget our notation here, right? So in the prior video we said that this was the slope of the tangent at a, right? This was the derivative at a, right? And then here we're looking at any value of x, right? So here's our f prime of x. Okay, so I'm going to do the best I can to kind of visualize, to animate this process, and it's a little bit difficult on a digital board without any real specifics, like a gridded graph paper, to be really precise. But I'm going to try to do this as precise as possible, but kind of focus on the concept, because that's really the main idea here. And then I have a cool little applet that I want to bring up that we'll take a look at. So here's what I'm going to do in this scenario. I'm going to draw a graph, and again, it's going to be a rough sketch. And here's the graph of a function that I'm interested in. Now, even though this looks like the parabola, y equals x squared, for a moment, let's pretend that it's not. And I just want to look at the shape of the graph. All right. So just to give myself a little bit more room here, right, I'm going to shorten this y-axis. Right? So it looks something like this, right? So here's my x-axis and here's my y-axis. And what I want to do is below this, I want to put another coordinate grid and I want to draw the graph of the derivative. So this is, and again, let me be a little bit more specific here. If this is the graph of f of x, right, what we're doing is plotting the graph f prime of x for any x value here. Okay. All right, so here's our graph of f of x. So let's think about what the graph of f prime looks like. So for example, let's suppose I come out here and I look at, let's say, x equals -3. What I'm going to do in that case is correspond to x equals -3 on the graph of the derivative. Now remember, the derivative of this function is the slope of the tangent. So again, without any real gridded paper, I'm going to roughly sketch a tangent line here. So let's say there's my tangent at x equals -3. And then if I plot the tangent here, it looks roughly, again, rough sketch, or roughly something like that. And then at -1, I plot a tangent, and it looks roughly something like that. Now, if I compare these slopes, right, again, my graph got a little cluttered. I don't have exact measurements, but notice that the slope here was a little steeper than the slope at -2, and then the slope at -1 was even less steep. So when we start on the left-hand side, we have a relatively steep slope. We have a slightly less steep slope, and then we have an even less steep slope. And when I get to 0, it looks like I have a horizontal tangent. So I have a slope that's 0. Now again, I don't really know what those numbers are, but let's pretend. So let's pretend at -3, the slope of this line is, I don't know, -5, let's say, something like that. So what I'm going to do is come down to my derivative, and at -3, I'm going to plot a y value of -5, let's say. So here's that y value of -5. So when I'm constructing the graph of the derivative, I'm plotting the slope of every tangent line. So again, if I'm looking at, let's say, -2 on the original function, I draw a tangent line, I calculate that slope. Now this is a little less steep than the one prior. So if the one prior was -5, I don't know, let's say this slope is -3. So at this x value of -2, the slope on the graph is -3. So I'm going to come down to my function and plot a y value of, let's say, -3. And then I would continue that process. So I'm plotting the value of every slope. So when I'm at x equals -1, I come up to my original function, draw a tangent line. Again, this is obviously a negative slope. But in relation, right, because I'm not really measuring precisely, right, in relation to the prior slope, this is a little more flat, right? So it's not as large an absolute value. So it is negative, but it's a slightly flatter line, a slightly smaller slope. So if this slope was -5, and we said this slope was -3, then let's say this slope here is -1. So at this x value, I'm going to come down to my derivative, and I'm going to plot a y of -1. And then if we continue with this for a moment, here at x equals 0, I can see the horizontal tangent that I have at that point. So remember that a horizontal line has a slope of 0. So my slope of 0 will become the y value of 0. So there's the first 4 tangents. We've calculated their slopes, and then we plotted those numbers. So again, at this point, the slope was, we said, -5, so we plotted a y value of -5. At -2, we calculated the slope. We pretended it was -3. So then we plot that y value of -3. Repeat that process, right? At -1, we pretended that value was -1, right? So we have lines that slopes are getting flatter, right? Smaller. So I have a smaller slope in absolute value. So a slope of 5 is pretty steep. A slope of 3 is a little less steep. A slope of 1 is a little less steep. And these are all negatives because the lines are decreasing. And then again, at the origin, we have a flat line. The slope is 0, so we plot that. Now, it's difficult for me to animate this visually, right? But if I had a kind of continual motion tangent line as it moves through this graph, every single point along this segment of the graph has a tangent and a slope to that tangent. So technically, right, every tangent exists in the domain of that function. Right? So I have infinitely many tangents, if you will, nestled around the 4 specific ones that I calculated. We get a smooth, continuous curve. And then in terms of this construction, we could continue in the same manner. So let's say look at x equals 1, x equals 2, and x equals 3. Now, so here's a slope of 0. So when I move here, I now have a slope that's positive, and it's a relatively small number. Let's pretend this is positive 1. So I'm going to come down to my derivative, and at this x value, I'm going to plot a y value of 1. And then if I come out here to x equals 2, I'm going to come up, draw a tangent, and I measure its slope. Now this slope is a little steeper than this slope, right? So this is a bigger number in relation to the one prior. So if we pretended this was a slope of 1, let's pretend this is a slope of 3. So I'm going to come down here, and I'm going to plot a slope of 3. And then we could continue in that same construction manner. So I'm looking at the x value of 3 now. Right? So if I look at my original function, I draw its tangent, I measure its slope. Again, notice this is steeper than the one prior. So if this slope we pretended was 3, let's pretend this slope is 5. So I'm going to come down to my derivative, I'm going to plot a y value of 5. So in this example, I have picked specific slopes and plotted them below, but again, as I animate a tangent line, there's tangents along this section of the graph everywhere. At every point there's a tangent. At 0.5 there's a tangent. At 1.8 there's a tangent line. At 2.9975 there's a tangent line, right? So I have continuously many tangents on that graph to create the graph of f prime. So again, as a quick review, conceptually in this section, what we are doing is we are graphing the slope of every tangent line. And as we plot the slope of every tangent line, we create another function. Right? So if I have a graph f of x, then my derivative f prime of x is just that. It is a function for any and all x values. Alright, so I wanted to bring up this cool web-based animation. This is on StewartCalculus.com from Stewart's textbook. And this does a visualization of animating the tangent lines. So it's pretty cool. I just want to show this to you. So at this particular x value, whatever this is here, let's say negative 1.2, whatever this x value is, right? There's the y value. And we're going to draw the tangent line. Now what's cool on this tangent line is they're kind of drawing a triangle for me. So here's the rise, right, my vertical rise, and here's my run, my slope. And they're trying to show me that over here visually in a quite precise manner, unlike we did on our board. So they're calculating the slope, right, rise over run, and we're plotting that value here of about 7, it looks like. Now, what we did in our example was we jumped, right? So if we were at like, negative 1, we went to negative 2. But what this is going to do is animate all the slopes. So I'm going to grab this line, this button here, and I'm going to slowly drag it to the right. And it's going to animate every single tangent on this graph. Now, as it animates the tangent, it's calculating the slope of that tangent and plotting it on the graph below. So I'm going to slowly animate this, and we can see it plots the slope of every tangent. Let me stop here. Let's say this is negative 0.8 on the graph, something like that. So I come up to my original function, I draw the tangent at that point. I calculate the slope of that tangent. Again, over here, they're showing me rise over run. So if I calculate the slope of this tangent, that numerical value gets plotted on the graph of the derivative. It looks like this is about 2.1-ish, let's say. I could get out a calculator and divide those and find out what that y value is. Oh, it looks like they're actually showing me the y value. Check that out. I didn't notice that before. Okay, so there's the slope of my tangent. So I measure this tangent, rise over run, measures to be 2.4. So again, the slope of the tangent becomes the y value on the graph. So let me animate a little bit further and point out to you one particular point of interest right there. Right? So whenever I have a value where I have a horizontal tangent, right? So let's say, what's this x value here? Negative like 0.6-ish. Here we go. Negative 0.68 is the x value. So at negative 0.68, we end up with a tangent line that's flat. The slope of that tangent line is 0. So when I plot the y value of 0, obviously that's an x-intercept. So something that's kind of neat here, right, as I do these problems in this section, the first thing I'm going to jump at are the horizontal tangents. And if you keep in mind on, this visually, intuitively, this makes sense. At a maximum value, right, I'm getting a horizontal tangent. At a minimum value on the graph, I'm going to have a horizontal tangent. So right here at x equals like 0.3-ish, I'm going to have an x-intercept down here because the slope is 0. So my y value is 0, and there's an x-intercept. And then again, as I animate the tangents over here is another horizontal tangent. That's going to correspond to an x-intercept there. So let me go ahead and grab this bar and animate a little bit more. So notice on this segment of the graph, the slopes were all positive, and we can see all the positive y values here. And then now the slopes are going to become negative, and we can see all the negative y's. So we're existing in the negative y-axis down here. And then I come back to the 0 slope at the minimum, and we can see that x-intercept that we have here. And I could continue animating in this manner. Slopes become positive, and then they go back to 0. Now I want to back up for a second and talk about this little segment. So here we start with a slope of 0. That's an x-intercept. Now as we slowly move to the right of that point, the slopes become positive, and they're relatively small numbers. So we look down here, the slopes are positive y values. So I have y values that are positive, and they're relatively small positive y numbers. It looks like between 0 and 1 are my slopes here. As I continue to animate this point, the slopes get bigger in a positive direction. So the slopes, the y values on this graph are getting bigger and bigger in the positive direction on the y-axis here. Now if you notice, this is kind of the steepest tangent line, and then they go back to 0. Right? So here's my steepest tangent line, and then they get flatter and flatter and flatter. So we can see that steepest tangent line gives me the largest y value on my derivative graph. So here's my largest y value. That's my largest slope of the tangent. And then the slopes start to get smaller again and go back to 0. So we can see the y values starting to get smaller and smaller and go back to 0. So again, that's what I was trying to do on this original graph here. It was difficult for me to animate this picture. So this applet's really cool because it animates that picture for me. So if I move to the right of this horizontal tangent, the slopes are going to become negative again. They're going to start off small, and then they're going to get bigger and bigger and bigger, steeper and steeper and steeper, in the negative direction. So they're going to start off with small y values and get bigger and bigger and bigger, and then they come back to 0 as the lines get flatter and flatter, right? So as my tangent gets flatter, I get y values that come back here. So this is the idea, right? So for every possible x value, we have a slope of a tangent, and we're creating the graph of the derivative down here. We have plotted the slope of every single tangent line to create the graph of the derivative. Now if we look at this application, this applet, they put some crazy function there just to give us a whole bunch of curves on that graph. If I look at another example, here's an example where there's a whole bunch of curves. Now again, if I'm asked to sketch this by hand, which I will in just a moment, notice that this is a minimum value. There's a horizontal tangent, so we're going to end up with the x-intercept here. Right? This is a maximum. There's a horizontal tangent, so we're going to end up with another x-intercept here. Right? Here's a horizontal tangent. We're going to have an x-intercept. And as I drag this line, it's going to move quickly. Right? So notice where we're at, the slopes are positive. So we have a positive y value. Pretty quickly, we're going to get to a 0 slope right here. So let's jump to that 0 slope, and there's my x-intercept. Now again, the graph starts to decrease, right? So I get negative tangents, negative slopes to my tangents. So I'm going to dip into y's that are negative here. So I dip into y's that are negative. Right about this point, I get the steepest slope. So I get the largest negative y number. And again, I want to be careful when I say the largest slope, right? The steepest slope, the largest value is really absolute value. Right? So the slope of this line is 3, but it's negative because it's a decreasing slope. The line is decreasing, right? So I'm getting the largest negative number, right? And large meaning absolute value. And then my slopes start to get flatter again and go back to a slope of 0 at my horizontal tangent. So again, the y values become smaller and smaller in absolute value, and then I hit a slope of 0. And then we could just animate this, and we can see, you know, all of those slopes plotting, and there's the graph of our derivative. Right, so applet's really cool. I love that applet. Just had to show that to you to try to animate the example that we were looking at. So the kind of the last thing we want to talk about in this section then is, so first of all, part of the conversation is I don't know the equation of this graph. I really don't. I'm not supposed to know the equation of this graph. So if we did that construction of calculating slopes, plotting those as y values, we can construct the graph of the derivative. But you know, just for fun for a moment, right, in the prior video we talked about manipulating a formula, right? So in the prior video we actually went through the algebraic work of manipulating this formula for a specific value of a, right? So we might have had a being 2. We were looking at x equals 2. So let's just remind ourselves it's almost identical what it would look like to go through this process. So what it would look like to simplify this formula for a specific equation. So instead of looking abstractly at graphs, let's look at the specific equation of y equals x squared, and what would the derivative of that equation be? All right, so again, for this example, and I'm pretending now that I know the function had an equation f of x equals x squared. And what we want to do is we want to find the derivative for all values of x. Right, so again, that's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay. So we're going to construct this difference quotient and then do a limit. And you know, if I've shown in prior videos, I like to do a little bit of side work first. I like to calculate what that numerator is going to be. So what is f of x plus h? Well, in this case, I'm plugging x plus h into my square function. So I'm going to get x plus h squared. And then if I, you know, FOIL that out, I get x squared plus 2xh plus h squared. So what I want to do is take f of x plus h and subtract f of x. Right, so let's say I take f of x plus h and I subtract f of x. So I get the x squared plus 2x plus h we just calculated, and I subtract the f of x. Again, I'm putting parentheses around this just to stress what I'm doing. Here's my f of x plus h. Here's my f of x. When I subtract those, notice the x squareds are going to cancel out. So I'm going to end up with 2x plus h. So this is my numerator of my difference quotient here. So I'm going to come back then and let's re-evaluate the limit. So we have the numerator over the denominator, right? And h goes to 0. Now remember, with direct substitution, right? Normally, oops, I'm sorry, I have left off an h here. I have a typo, right? This was 2xh plus h squared. I was having a little too much fun here, and I forgot to put that term. Right? Let me come back and fix that. So I have 2xh and then plus h squared here. So this is really 2xh plus h. So I had a little typo there. I guess technically this isn't a typo, is it? It is a writo, because I'm writing. All right, so let me fix this one then. So we really have 2xh plus h squared as our numerator and our difference quotient. So back to what I was about to say here, right? So normally we direct substitute. We plug in h equals 0. And again, if I plug in h equals 0, I'm going to get 0 plus 0 all over 0. Obviously, we can't evaluate division by 0. So what we talked about in the prior videos is we would do some algebra. So I'm going to factor in h out of the numerator. I'm going to have 2x plus h left over when I do that. And I have forgotten my limit symbol, right? Technically, I have the limit that I'm carrying along here. The h's cancel, so I end up with the limit of 2x plus h as h goes to 0. Now I direct substitute, and I end up with 2x. So if I have an equation, and I'm finding the equation of the derivative, right, it would be identical to what we did prior. We're just letting x be any arbitrary value. Now, if I scroll back up real quick, bear with me for a moment. Here was the x squared that we had. This looks kind of like the line y equals 2x. So we can see from our formula, right, that the derivative of the quadratic was something that looked linear. And of course that should happen, right? So whether we construct slopes of tangents to plot y values on the derivative, whether we take that process or we look at the equation, right, we should be getting the same relationship. Okay. So let's do a couple more examples here. Actually, wait. I'm having so much fun, I'm forgetting what I want to do. What I want to do is look at one last concept here. And that being, when would the derivative be undefined? Right? So let's ask the question, when is the derivative undefined? When is f prime undefined? Right? Now, without, that needs a question mark, doesn't it? Without getting too gory into details here, let's just talk kind of big picture, right? Let's talk conceptual again. So if I think about what does that mean? What does it mean for the derivative to be undefined? Well, let me scroll back up for just a second here. And let's think about the definition of our derivative, right? Here's the definition of our derivative. So when is this going to be undefined? Well, the only time it's going to be undefined is really when this limit doesn't exist, right? Notice this is a two-sided limit. So as h approaches 0 from the left and as h approaches 0 from the right, those one-sided limits have to be equal to each other, right? They have to exist and be equal to each other for the two-sided limit to exist. So if this two-sided limit doesn't exist, then the derivative is not defined. So when is f prime undefined, right? The answer being when the two-sided limit as h approaches 0, right, does not exist. I'm going to get lazy and say D and E. Okay. Now, visually, right, what are some situations where that might occur? So visually, here's one situation where that might occur, and this is a really classic example that I want to discuss here, which is the absolute value function. So let me switch back to blue and let's look at the absolute value function. Right? Now, if we go through that same process that we just did, and we, let's say, construct the slopes of the tangents. Right? So I'm going to construct the slopes of the tangents. Right? Here's the graph of f of x, right? And I'm going to graph the derivative f prime of x. So again, I'm going to pick, let's say, x equals -3, -2, -1. So if I come up here and plot a tangent and I find the slope, notice that this is already, right, absolute value of x as a linear function. So the slope of absolute value is -1 here. So the slope at -3 is a value of -1. And then ditto here, right, when I look at this x value of -2, I come up and plot, this is a linear function already, so the slope of this tangent is also -1, so I'm going to plot that value. And then when I come here, I plot another tangent. So if I look at x equals -1, plot the tangent, it's a linear function, it's the same slope as before, it's a value of -1. So all of the slopes here are values of -1. Now, real quick, let me jump over to positive x's. So if I plot a value of x equals 1 or 2 or 3, so if I pick x equals 1 and come up here and draw a tangent, that slope is positive 1. So here, my slope is positive 1. And then if I look at, let's say, x equals 2, come up, draw that tangent, that slope is also positive 1. So there's that slope. If I look at x equals 3, come up and plot that slope is also positive 1. So I'm looking at this graph. Now, here's the question, right? What happens as we approach the origin? Well, if you think about this for a moment, let's see if I can sort of animate this with my pen. I'm going from x equals being negative, 0.9, negative 0.8, negative 0.5, negative 0.1, negative 0.01, negative 0.001, negative 0.0000001. All right, so as x approaches 0, right, all of these slopes are negative 1. So my graph is getting closer and closer and closer to here. Ditto, as I approach 0 from the right, 0.5, 0.1, 0.01, 0.01, all of these slopes are positive 1, so I'm getting to that direction. Now the question then is, what happens at 0? And here's the difficulty with that answer, and this is where the limit will fail. So let me see if I can just kind of exaggerate the absolute value here. So the question would be, right, like, so what does the tangent look like there? And the reality is there's infinitely many tangents. I could plot a tangent that's 0, and I make a glancing blow to one point. I have a tangent that does a glancing blow at one point. I could also draw a tangent this way that has a glancing blow at one point. I could also draw a tangent this way that has a glancing blow. So in other words, there's infinitely many tangents occurring at the corner on this graph. This two-sided limit is failing when x is equal to 0. So what happens then is we have an undefined point on our derivative f prime. So what I'm trying to connect to here, by using the absolute value function, because it was easy to find the slopes for both sections, is that when we get to the corner, the derivative is undefined. So in a very general manner, we can say the f prime is undefined or does not exist. Right? F prime is undefined at a corner. So anytime we have a corner, we're going to have some form of a discontinuity on our derivative. Right? In this particular scenario, we have a jump discontinuity. Right? But anytime we have a corner, we're going to have the derivative being undefined. The graph of the derivative would be discontinuous. So, what's another scenario where we could see a derivative be undefined? Right? Well, I say obviously, right, but maybe it's not so obvious, right? But if we think about a graph where, let's say, we have a vertical tangent, right? Here's a graph. I'm just going to draw some shape of a graph that has a vertical tangent. And then I'm also going to draw a graph that has its own discontinuity. And then I'm also going to draw a graph that has another discontinuity. Let's say something like this. Okay? So here's a graph of a function f of x. And at all of these discontinuities, the slope of the tangent doesn't exist. Right? Now, obviously, if this x value on the function doesn't exist, right? There's no y value that I'm plotting here, then there's no way f prime is defined at that point. Right? So anytime I have an asymptote, right, and that's a vertical asymptote in particular, right? Anytime a vertical asymptote, the function isn't defined there, right? So the derivative isn't defined. Now, when I look at this point over here, technically the function is defined at this point, right? We've plotted a y value. But very similar to the absolute value function, look at what's happening with our tangents as we get close to this x value. From the left, my slopes are all positive, and then from the right, the slopes are negative. So we're getting that kind of jump discontinuity that we had before. Right? So in an asymptote or a discontinuity, we're going to have places where my derivative is undefined. And then ditto here as well, right? So at this point, the function's not defined, right? But it's also classified as a discontinuity, right? So I'm going to just say the function's not defined. So an asymptote is a place where a function's not defined. Those are really kind of analogous, kind of the same thing, right? But visually they look different, right? So an asymptote is where a function's not defined. The derivative won't be defined there. The hole in the graph is where the function's not defined. The derivative won't be defined there. And then any, discontinuity, in this case a jump discontinuity, the derivative won't be defined either. There's one other visual scenario where we could see a derivative not defined, and this one's a little odd. I'm going to try and exaggerate this. So let's say I have a graph, and let's say that it comes in and becomes purely vertical for a moment. So if I think of a tangent to this point is completely vertical, and remember that for any vertical line, the slope of that line is undefined. So my tangent will also be undefined at that point, right? So f prime is undefined at a vertical tangent. So in a visual manner, those are the three places in particular, right, where we would find the derivative is undefined. Right? We would first of all have a corner. Right? So a corner is where the derivative would be undefined. We use the absolute value function to illustrate that. Points of discontinuity is where the derivative would be undefined. And then at a vertical tangent. Right? Okay, let's get a little bit more practice with this. All right, let's take a look at this example. And what I want you to do for me, based on everything we've talked about up to this point, I want you to pause the video. And I want you to try to do this problem without me first, and then we'll go over this together. So here's what the instructions say. Right? The instructions say the graphs of A through D, right, are given. And these are the functions. So this is some function f of x, and somewhere over here in the Roman numerals is its derivative. So again, letter B is a function f of x, and somewhere over here in the Roman numerals is its derivative. So the derivative is in the Roman numerals. So pause the video for a moment and see if you can match which function goes with which derivative. All right, so you've unpaused the video, and we're going to talk about this now as an example. So I mentioned to you that some of the particular points of major interest are, horizontal tangent. So the min or the max value is a horizontal tangent. So for this particular graph, right, if I'm trying to sketch its derivative, I can see somewhere out here, I don't know, x equals -1 or something like that, x equals +1. These have slopes that are 0. So those are going to be x-intercepts on my graph. Now if I come over here, I can see here's x-intercepts on my graph that correspond to that. I also see x-intercepts on this graph that correspond to that same behavior. Now, if I jump back in this direction, if I animate my tangent, if there was any way for me to animate my tangent, the slopes of these tangents are negative. They're pretty steep, so that gives me pretty large negative y values. And the slopes stay negative. They get flatter and flatter until they come to a slope of 0. So the m values are getting smaller and smaller. The y values are getting smaller and smaller and hitting 0. Again, when I say smaller and smaller, I'm meaning in absolute value. Right? Now, if I look again here, as I move slowly to the right, the slopes become positive. They're kind of small. And then they become bigger positives. And then they become smaller and go back to 0. So I have slopes that are becoming slightly positive, bigger, and then back to 0. So here's slightly positive, here's the larger positive y's, and then here's the y's getting smaller and going back to 0. And then again, on the last piece of my function over here, the slopes become negative again, and they get larger in the negative direction. So here's our y's. So the reason this graph didn't match is it had one more 0 here. which we don't see on this graph. Another reason that it didn't match is these tangents started out as negative slopes, and these points don't start out as negative y values. They're positive y values. So there's no way this graph could match that derivative. So I'm going to pick red, right? And A goes with graph 2. Right? Now let's do letter B. Let's do these in order. So this is kind of like my absolute value function, right? Notice that there's a corner 2 places on this graph. So the derivative is going to be undefined at 2 places. Now because this is a matching, I can see here's 2 places, here's 1 and 2 where the derivative is undefined. Now also we notice this is a linear function, right? So the rate of change of this line is constant. It's the same everywhere. So we can see the rate of change staying constant, rate of change staying constant, rate of change staying constant. Another reason why those match in that scenario. So let me use what I used before. Let me use green. So letter B goes with letter 4. So let's look at graph C. So we'll look at graph C. Again, I'm going to jump to the horizontal tangent. So right here is a horizontal tangent. So when x is 0, I have a horizontal tangent. Now with the 2 graphs that are left, I haven't chosen this, these or this, right? So here's a value of y equals 0, and here's a value of y equals 0. So again, when x is 0, the slope is 0. Therefore, on the derivative, the y value is 0. So I see both of these exhibiting that behavior. Now, if I come out here to the far left, right, let's say these slopes are relatively flat, not exactly 0, but they're pretty small. And I can see on this graph over here, these y values are almost at 0, right? They're pretty small and they're negative, right? Just like these are decreasing slopes. So the slopes get larger and larger, right? The line gets steeper and steeper, but then it goes to 0. These are all negative slopes. Start small, get bigger, back to 0. So here's small y's. The y's get bigger, they go back to 0. Again, these are negative slopes, and I don't see negative y values on this graph. So these have to match each other in that sense. Now, let's just finish the graphing though, right? So here's a slope that's 0, here's a y value that's 0. The slopes become positive, and they're relatively small, and the slopes get steeper and steeper, and then they go back to 0. So my y's start small, they get bigger, and then they go back to 0 here. And again, process of elimination is that D is going to match with 3. But again, let's make the official connection, right? So here's a slope that's 0. So at this x value, there's that intercept. Right? Here's another slope that's 0. So at the origin, there's another x-intercept. Here's another slope that's 0. So that at that x value, there's that x-intercept. Right? So we can see visually we're getting that behavior. The slopes are all positive and pretty large. So here's my positive y's that are pretty large, and they're going to decrease to 0. So the slopes get smaller and smaller and smaller to 0. And then the slopes become positive. They get kind of large and back to 0. Oh, I'm sorry, I said that backwards. The slopes are negative, they're decreasing, and they go back to 0. So negative, and then they go back to 0. Slopes start to increase again, and then they go back to 0. They are positive, go back to 0, and then the slopes become negative as the graph decreases and get larger and larger. Okay, so here's the next example I want to look at. And again, I want you to pause the video here and try this on your own first. So this is like the very first example that we did. And we have the graph of a function here. And below, I want you to do your best, right, to construct the graph of the derivative. For this graph, you're going to construct the graph of its derivative below and then repeat here. So pause the video and try that on your own. Alright, so now that you have unpaused the video and we're going to work on this together, we're going to talk about what you saw. So this is identical to the first example. And again, when I'm doing these constructions, I'm jumping to the max and min values first. So I can see right at x equals 0, there's a horizontal tangent. So at x equals 0, I have a y value, which is 0, because it matches the slope. And I'm going to kind of move, I'm going to jump back over here and I'm going to slide in this direction. So initially these slopes are negative and they're kind of large, and then they move and get smaller to 0. So they're kind of large and they move and get smaller to 0. And then the slopes become slightly positive. And then the next one is a little bigger positive value, and the next one's even bigger positive value. And there's roughly the sketch of our derivative, just like our first example. Now when I look at the next example, again, I'm going to jump to the maximum and value. So right about here on this x value, I see a horizontal tangent, so that's an x-intercept. And then over here is another horizontal tangent, so that's an x-intercept. Another horizontal tangent, so that's an x-intercept. Another horizontal tangent, and so that is an x-intercept. Now, if we look at this segment here, right, the slopes are positive and they get smaller and go to 0. So the slopes are positive and they get smaller and go to 0. So I'm getting that shape of a graph. Now, when I come back up here, I move to the right. They become negative. They're kind of small. They move to about the middle here and are their largest, their steepest slopes, and then they come back to 0. So they're negative, they get large, smack in the middle, and then they come back to 0. So we're getting that sort of a shape. And then notice that this graph is kind of like a trig function, right? It's periodic. So we're going to repeat that behavior. So again, here's my x-intercept, right? Horizontal tangent. I get slightly positives. They get bigger slopes, and the slopes go back to 0. So slightly positive, bigger slopes, and then the slopes go back to 0. And we would continue repeating that process. There's a rough sketch of the graph of the derivative. Now something that's kind of cool, right? Doing a little bit of foreshadowing here to the next chapter, if you will, some of the videos in the future. What we see in this case is kind of like a parabola, and we see its derivative being linear. So what we'll see in the next couple of videos, we're going to look at some shortcuts for finding these equations. A quadratic becomes a linear derivative. So the exponent gets reduced by 1. We're going to see that as a shortcut pattern. This graph is actually the graph of the sine function. And notice this graph is the graph of the cosine function. So when we do the shortcuts, we're going to make the connection that the graph of sine is cosine. The graph of a polynomial is another polynomial with the power reduced by 1. Now in this example, we don't have a specific equation for this example, so let's just go back to the construction process. So notice I don't have any specific rounded max or mins. I have some corners. Here's a corner, so the derivative is going to be undefined. Here's a corner, derivative is going to be undefined. Here's a corner, derivative is going to be undefined. So I don't really have values that would be x-intercepts to jump to first. So let's just go from left to right. So this segment of the graph here it's a line, right? So it has a constant rate of change. And these would all be slopes of 0 here. So the derivative is going to have all y values of 0. And then at the corner, it's an open hole, it's undefined. Then all of the slopes are, well, what are these slopes? We could actually calculate these slopes, couldn't we? So from this point to this point, I have a rise over a run. So I have a rise of what? 1, 2, 3, and a run of 2. So 3 halves is my slope. 1.5 is my slope. So here's my slope of 1.5. Again, this is a corner, derivative is undefined. Oops, I went too far. Here's the x value where it stops, so it's undefined here as well. Let me fix that. All right, and then this segment, again, the slopes are all 0. It's undefined here, right? And the slopes are all 0. So there's the first segments of the graph. All lines, all constant rate of changes. Here's my constant rate of changes. Now over here, we have a graph that's curvy, right? Obviously this is not linear. These rates of change vary. So let's plot this curvy derivative, right? So just to the right of this undefined value, the tangents are negative and they're pretty big. So I have a pretty big negative here. And then the slopes get slightly less steep, so the negative value gets a little smaller, right? And then again, the slope is negative but a little smaller. And notice the slopes never really go to zero. I never really get a turning point, right? A minimum. They just become smaller and smaller negatively. So I really kind of have an asymptote horizontally in that manner. So there's the graph of the derivative in that segment of the graph. Alright, this video is getting a little long. I prefer my videos to be 30 to 40 minutes at the most if I can't make them shorter. And this one's getting a little long. Let's look at one last example. And in this case, let's focus on the instantaneous rates of change and their units, right? And how we're going to interpret this. Because remember, ultimately, our application of derivatives is that a derivative is a rate of change. So we're going to look at word problems. We're going to look at applications. We're going to discuss those rates of change and what they measure. Now, in the prior video, we did have that conversation. We talked about what rates of change look like in the fields of biology and engineering and physics and chemistry. So let's just look at one particular example and just come back and refocus that conversation. So this problem says that a rechargeable battery is plugged into a charger. The graph shows C of t, right, the percentage of full capacity that the battery reaches as a function of time in hours. So as the battery charges, we can see the graph increases. So it gains voltage, or it gains kilowatts charging the battery. And obviously the battery must hold a maximum of 100 as a percentage of capacity, right? Once the battery's full, it's 100% full. So it's approaching the 100% value. I guess this isn't kilowatts. I don't know why I said that, right? This is percentage full. So letter A says, what is the meaning of the derivative C prime and what are its units? Right? So again, the meaning of the derivative is it's the instantaneous rate of change. If we think back into a physics problem, right, that's feet per second, miles per hour. It's like our velocity. So this is really the rate at which the battery charges, right? So it's the rate, or the speed the battery charges. And then what are the units, right? So remember, the units here are delta y over delta x. Those are the units. So y units per x units. So we have percentage per hour, right? Those are going to be our units. Percentage per hour. Letter B says sketch a graph of the derivative. So I don't have these lined up together, but let's think of what we just discussed. So initially the slopes are pretty large. They're positive. So initially here in the beginning the slopes are pretty large, positive. And then as I move, the slopes are still positive, but they're getting a little flatter and flatter and flatter and flatter and flatter. So the slopes stay positive, but they get flatter and flatter and flatter. The slopes never really reach zero if this is an asymptote, but they do get really, really small. And there's a horizontal asymptote in that manner. So there's the graph of our derivative. And letter C says, what does this shape of the graph tell you as t increases, as time increases? So if you think about this, the charge starts off pretty large. The y's are large. And then the charging slows down, right? So the capacity of the battery, what it can absorb, starts to slow down. So the charges are growing quickly. The y's are large, right? The speed of charge is large, and then the speed of charge is small, right? So we could interpret that something like the charging capacity starts large, let's say, right? Charges quickly. Then the rate of charging slows. Let's say as the battery gets full. Right? All right. So this is the end of this video here. Let me end this. And in summary, right, we've talked about derivatives again as rates of change. Instead of finding slopes at a single value, we're finding slopes at all possible values in the domain of the function. We're sketching the graph of that derivative. Based on the definition of the derivative that we wrote at the very beginning, right, we could calculate the equation of the function, but that's not really the focus here. That'll be the focus in the next couple videos that we will take a look at.